and then rearrange the bolts by
Rearrange.
quick sorting them. And then I would do it recursively on the left side and on the right side. And then it'll be nicely partitioned at the end for both nuts and bolts.
Okay, perfect. All right, so everybody understand? So Dajang's approach is pick the bolt and then go to the nuts shack and keep comparing. If it is smaller than me, go to left. If it is larger than me, go to right. And if you find it, okay, there it is. When the new So can you see my screen? I think so. Okay. All right. Right? You can see my screen, my slide. Right? No? I'm struggling again. No. Sure. Okay, so the same things. So keep repeating, but on the second one, you are just visit this one first. Therefore, you know the where to go, okay? And there, you'll find your position and you are keep comparing it, go to the left and right, left and right, and left and right. So in the first shot, you make halving it, left and right. Then from there, as you're using this one as a pivot, you can divide and divide and divide it. Therefore, you can find what's the complexity of this?
And log n.
And log n. Okay. Why? Because in the first one, you have to run once. Then after that, you are keep comparing it one by helping it and helping and helping it. Therefore, there's n log n. All right, great. Anyone else?
Professor?
Yeah.
My approach was using a hash table.
Hash table, okay.
Yeah, so.
Who's this speaking?
This is Yongho.
Yongho. Yongho?
So I don't think, yeah.
Okay. All right, go ahead.
So I think complexity would be ON for hash table because first I make a hash table for nuts. And then after
how can you make hash table for n? Because we don't know. We cannot compare it by looking at it.
Oh, I thought the size of the nuts.
So it says the size between pairs of nuts can be too small, cannot be seen by eye. So if you want to sort them first with the nuts, right, then that is impossible by the assumption. Good try. You can try if you can continue your voice, please. You may continue. Go ahead. Yongho? Am I lost again? No? No response? Hello?
Yes, Professor?
Yeah, so you may go ahead. You may continue, whatever you want to.
Okay, so my approach was traverse the set of the nuts and make the hash map. And then with that hash information, I compare it with the bolt. Yeah, that was
good approach. But the assumption we are using this, we cannot build a hash table with only bolt because we have no knowledge to compare it size by size with only nuts. Okay, good try. Okay, good guys. And then we can solve this by n squared, something like insertion sort or selection sort, right? Comparing one by one and dividing it and keep looking for it, like a bubble sort is n squared. I'm looking for that and next spot and looking for that again, looking for that. That's bubble sort. How about second problem? So third problem, we solved this. That's a notes. The Tajong solved this. The second problem is, suppose that instead of matching all the nuts and bolts, you wish to find the smallest bolt and corresponding nuts. And showing that can be done in 2n minus 2 comparison. So now you understand. Previously, I have to find all the matches, but this is asking you that to find the smallest one, just once. How can you find the smallest one so quickly and so efficiently? Let's think about for 1 minute. Then I'm gonna ask Hotaejun and PK. I think Taeyong dropped the class, right? She dropped the class. Ready? Taejun? Taejun not here? Maybe PK? Anyone else? Anybody?
Sir, can I try? This is Jong-hoon.
Sure.
I will pick random nuts and random nuts and random bolts. And if bolt is larger than a nut, then pick another bolt. And if nuts is larger than a bolt, change another nuts. And if we repeat it, I think I can find smallest bolts in 2n comparisons.
Perfect. So everybody understand? So I have 2 sec and pick the random one and keep comparing it on the right side. If you find the match or the smaller one, then you can keep replacing it. If you find the smallest to fit in the bolt, then you throw the bolt again, then you keep comparing it. Then if you find the which is smaller than this, and keep the throw the nuts again, and you keep playing with this, then in the end, the activity you are throwing away is except the one last match, the minimum one. Then everything is thrown away. That is why n, and the last one, right? So therefore, it is a 2n minus 2. Okay, so we talked about the n log n. The Tajong gave a perfect example. And randomize the quicksort. We talked about quicksort last class, right? So randomized pivot is critical. Why? Because let's say your algorithm is tested by your biggest enemy. And what they're gonna do, they'll give you the worst case, which is the pivot is, if they know your pivot selection process, and they will give you the reverse order of it. But by selecting a random, whatever they figure out, but it doesn't matter because I'm using random too. So we can say that with high probability, randomized quicksort runs in n log n. Okay, so before we said that if you give me a random input data, quicksort runs in, if you give me a random input data, then I can run n log n. Then your enemy said, I'm never gonna give you a random set. I'm gonna give you the intended set, right? So rather than doing this, we can say with high probability, randomized quicksort, because my quicksort is randomized, then it runs on n log n. So importance of randomization. So since the time bounded depends on your input distribution. So unless you are extremely unlucky, so expectation is n log n. So in reality, is a quicksort is faster than a heap sort. So we learned that heap sort is very efficient because we don't maintain the sorting. We don't maintain the tree. We don't maintain the our data structure tight enough. and in reality, quicksort implemented well, so it is usually 2-3 times faster than merge sort and heap sort. So that is why we call this quicksort. Why is this faster? Because if you look at the innermost loop of the quicksort, it is very simple. Pick, go to left and go right. That's it. That's it. Merge sort, you have to put in a bucket and you do something, right? And the bubble sort, you have to keep comparing, keep comparing. The quicksort is pick it, left and right. Very simple. Therefore, it is implementable in an assembly level, then therefore the efficiency of the program increases. And sorting and tree. So any comparison-based sorting can be thought of as a defining decision tree of possible execution. So decision tree. Am I bigger than this? Go to right. Smaller than this? Go to left. Decision tree. Every point you make decision, left and right, right? Running the same program twice on the same permutation causes it to do exactly the same thing. But running in a different permutation on the same data causes different sequence of the comparison be made on each. Which means based on your insertion sequence, based on the sequence of data, the insertion, your tree may be shaped differently. So something like this. So if you go to the A1 is a smaller, A2, A3, that 1, 2, 3, then you understand what it is. If it is all forced, A2 is a bigger, right? So A3 is bigger than A1, and A2 and A3 is bigger. So 3, 2, 1. So in a sequence, in an index. So height of index is what we are doing for the comparison. So what about dumb comparison-based sorting? We all talked about the comparison-based sorting. How can you do that? So how can you, you know the poker game, the poker card is A2, then T, J, Q, K, which is 13 per spade, diamond, heart, and clover, right? And how can you sort them? How can you sort your poker card? What is the fastest way to do that? What I do is I first throw into the spade, every heart, every clover, and something in this pattern. Then from there, I sort it in the number, Is it better than just sorting everybody in one shot? Do you think so? Why? Because I make the bigger problem to the smaller problem. Then from there, I try to solve it the smaller problem, right? Something like this. So let's talk about the bucket sorting. Bucket sorting is application of those things. So suppose you are sorting n numbers from 1 to m, where you know the numbers are approximately uniformly distributed. And we can set the n buckets, each responsible for the embodied interval of the m by n. So if the new member, I don't need to precisely do it. So if it is about there, I just throw it that bucket, that bucket, that bucket. Then what do I do? Inside the bucket, I sort it. Inside the bucket, I sort it. Then in the end, I can connect everybody. Completely sorted, right? So bucket sort in the first shot, I only do one time, which is like the hash code, the hash table, like for I do n, the hash. Rather than hash, I do bucket. Go to bucket. Inside a bucket, I do the sorting. Okay, read once, roughly put into the bucket, then from there you do sorting. So the first one takes only one time to the bucket. Then from there, you have to, so inside a bucket, you have to sort it. What's the complexity on this? Because you are such a small set, then I can do it in quickly. Find the minimum one, like insertion sort, selection sort, you can do that. Then the fastest to do it is proportion to n by n. Then we can say that then it is very small tight, 1 or 2, I can compare it in one n time. Why is it n time? I can do proportional to n by n time because the numbers I have to compare is very small. 1 or 2 or 2 or 3, I can do it in one shot. Then you can connect everything else. Then we go n. You know what? What happened to our n log n? You told me, I told you that the fastest sorting is n log n. Oh, we just did a big O n, which is faster than n log n. What happened to this? Because in the worst case, if there is an enemy, they'll put your bucket into that. So if your input is not evenly distributed, the bucket will be filled in. One bucket will be filled in, right? Therefore, that it will make the worst case. Worst case in this one, then in here I have to do sorting again, which is inefficient. So real world distribution. So like a bucket sort. So the worst case shouldn't happen if we understand the distribution of data well. Okay, consider the distribution of the names on the telephone book. Do you know the yellow page? Maybe you don't know the yellow page in your age, but there is a phone book. I can open the phone book and I can find the name and I can call it long time ago. And so all your privacy is leaked, right? Long time ago it happened. And it was very common all over the world. So is the name of the Simon, is it common? Roughly yes, but how about Smith? It should be very common, right? Like a Kim in Korea, very common. And how about Shiflet? It will be very rare. It's almost not happening. Like in Korean, like Ka. Do you ever saw the name the Ka? Like Kim and Ka is a couple of different story, right? It will be very rare. Okay. So what we are doing is bucket sort. So to do that, oh, it looks fine, and sorting is fine. I can put it the rare one and well distributed, then I can do that. But what happened in reality? So for the comparison, there's only Shiflet in 1000 page Manhattan Yellow page. But in the Charlotte bill, there's all Shiflet in a phone book. What happened to that? So we have to understand the data first, right? In a Shiflet, the whole family live in a Charlottesville. Yeah, something like this happened in reality. So whenever you do a sorting, linear sorting or quick sort, the sorting, whatever, we have to understand the data first. Then we can find the proper sorting mechanism which optimized for that data. Then we can do the better. Okay. This is what I prepared today. Then I think we can wrap up today. And sorry for the late class. And I will upload the, do you have a homework this week? I will check it and I will upload my video and slide properly. If you have a question, please visit my office or just call me on the Zoom. You can send me an email, and my door is always open. So you can visit my office. All right. Any comment? No? Okay, once again, I'm sorry for the late start, and thank you for participating. All right, guys, have a good weekend, even we are still Wednesday.